My name is Rugwama Walbero, and this is Squish, force input on soft surfaces for visual targeting tasks. This research paper mentions that most studies investigated force input on rigid surfaces. It also found that some work in human-computer interaction and material science proposed solutions to enable interactions on arbitrary surfaces. However, only few studies investigated force input performance on soft surfaces, and really none investigated the effect of the surface compliance on the user performance. It was then unclear whether interaction techniques developed on rigid surfaces would also be used on soft surfaces, which brought the question of how material softness affects interaction. Proposed solution. To address this gap in knowledge, they presented an experiment evaluating user performance of force input on soft surfaces for visual targeting tasks. They have designed a task that consists in matching a force level using a slider controlled by the force applied on 3 surfaces. They use silicone samples, and as it can be seen on this image, a sensor is located between the fingertip and the surface, and based on the softness of the surface and the force applied, it displays the material deformations. The work evaluation is divided into 3 steps. The first one is force input performance that studies the user's ability to select absolute force levels, and for this one, the participants use the finger on the surface and let the users define comfortable force ranges. On the second step, it was found that previous work on visual mapping did not discuss the output of the pressure sensors, which led the authors to use an amplifier to produce a linear output and allow them to show high precision rates. For the selection steps, which are dwelling or quickly releasing the finger from the sensor, it was unclear how they were implemented in previous studies so far. And to address this issue, they use an efficient way based on human model processor or CMN model. Contributions and process. They first presented the fabrication process of the 3 soft surfaces, introduced the pressure sensor, and then explained the calibration protocol. They use silicone because it is widely used as a material for creating soft interfaces, and it allowed them to create specific deformable surfaces. They also use interlink long-tail FSR 400, which is a commercial pressure sensor smaller than the fingertip because it was previously used on other studies. It is also important to note that both materials facilitate the replicability of experiments. As you can see on this picture, they recorded the sensor's output in relation with the force applied using a scale. And to perform the experiment, users control a linear cursor by varying the amount of force they exert on a soft, medium, or hard surface. They recruited 24 right-handed participants in the local university, and they were aged from 21 to 37. They also used 3 independent variables that are the compliance of the surface, the number of levels composing the scale, and the actual levels or targets. And as shown on this image, which is the representation of the interaction between the target and scale-independent variables. They have also evaluated the user performance with 3 metrics that are the percentage of correctly completed trials, for how long did the participant apply force, and how many times the participant entered and left the targeted level. To ensure that each participant could comfortably complete the experiment, they initially provided the maximum force level they could comfortably perform, and then the authors set this maximum value as the maximum of the force scales. They reported their results in emphasizing on effect sizes and confidence intervals. They therefore assessed the differences between 2 populations by depicting the differences of their means. As seen on image A, the participants were very accurate on every surface with an average success rate of 95.42%. And when multiple tests were performed using different scales as seen on image B, there was little evidence of better performance on the hard surfaces. The results as seen on the image below indicate that using the soft surfaces, the participants needed more time to reach the levels before releasing their finger. The authors observed that soft surface leads to more crossings only in high force levels. They have also observed little evidence of a difference between the soft and hard surfaces for medium values. User preference, and when participants were asked to ranked the surfaces. The hard surface was most frequently ranked first, and the soft surface was ranked second. The results then showed that participants found that soft surface to be more comfortable, but they perceived it as less accurate than the hard surface. They also found that the three surfaces were comparably demanding. In this section, they discussed the results of the experiment by focusing on two primary outcomes. They only observed a small effect of the surface compliance on the user performance, and also observed higher force input capacity than previously reported in the literature. They also observed a high accuracy with the denser scale, which contrasts with the results from the literature. And previous work reported user performance greatly decreases for denser scales. And by comparing most relevant previous work to the work as seen on the table, they noted two main factors that could explain the difference, which are the force range and the selection technique. It is found that systems that use force input are rare, and this is unfortunate as with force input, one could interact on the cheek or on the sleeve to control AR goggles and input text using force. They could also interact on the armchair of a sofa to control a TV, or leverage force input in the context of thumb-to-finger interactions as seen below. Implications. The author's analysis showed no evidence that soft is better for force input, but neither is it worse than rigid. This suggests that when designers choose the input device, they can focus fully on the user performances without worrying that choice of material will have a significant impact on user performance. However, to fully leverage this freedom of design, mapping and calibration should be given special attention in sensor implementations. So the final recommendation is to use the force because a powerful advantage of force over input methods is that it only requires fingertip size interactive areas, and it also leverages interactions. Limitations and feature work. The study focused on normal forces applied using the index finger. Hence, it is unclear how the results transfer to multi-finger interactions, like squeezing or pinching a material. They use silicone and a separate sensor. However, many soft interfaces have integrated sensor, and many other materials can be used. So feature work needs to be addressed on both mappings in more details to compensate for high forces on soft surfaces and likely enhance the input capacity. Analysis. I believe that this paper is good idea because in the future, input devices will be more diverse and will challenge designers to appropriate everyday objects for inputs, and this will be a good point in helping creating those devices. However, suggesting the use of cheek or thumb to finger as input device will require privacy, safety, and security implications that pose great challenges for the acceptance of this technology. There is a need for more information about the different types of technology that should be used. With that in mind, I'm left with questions like, is the implementation really going to work? Will people want to use it? And what exactly will it take to implement it? Conclusion, the authors presented a user experiment investigating the effects of surface compliance on force input for visual targeting performance. They concluded that results on previous findings on reduced surfaces transferred to soft surfaces. Based on those results, they presented use cases as examples to encourage designers to think beyond conventional touch input and leverage the power of force input of soft surfaces. Thank you.